So I want to get started now. So if you have your homework now, you can turn it in. If not, or if you haven't turned it in, you can also turn it at the end of class. Okay. So today we're going to continue talking about empirical methods in economics that we use to try to estimate relationships between variables. And so we spent like the last couple lectures talking about what this thing that's called the conditional expectation function is, what its properties are, and why we might want to estimate it. Basically, if we look at the conditional expectation of y given x, it will give us a sense of how, on average, y is going to change with a 1 unit change in x. But as we said at the very end of the last lecture, correlation doesn't imply causation. So just because you see that there's a positive relationship between two variables when you map out the conditional expectation function, or when you estimate a linear regression, you find an upward sloping line, that doesn't mean that x has a causal effect on y. So that's something that we're going to return to shortly. But first, I want to sort of talk about a couple of special cases of regression. So one special case that comes up pretty often, you'll see in this class pretty often, is a case in which the right-hand side variable in the regression x is binary. So remember, we're talking about a regression model that looks like the following. We're specifying the outcome yi as being equal to alpha, which is just some constant, plus beta x, where beta is the slope coefficient, if you were to draw a graph. And so beta is telling us how much on average we would expect y to change with a 1 unit change of x. But this relationship isn't deterministic, so just because x is equal to a specific number doesn't mean that we'll know exactly what y is equal to. So there's also some residual term, which we'll call ei or epsilon I, which basically represents the other components or the other things that are determining the outcome besides x that are sort of going on behind the scenes, but that we can't observe as researchers. So this is like this unobservable component, or this unobservable term that contains other determinants of the outcome. And so there's a special case when x is a binary variable that just takes on 0, 1 values. So like, when we're talking about the coin flips, in that case, if x was the outcome of a coin flip, then we'd probably code it as a binary variable, 0 if it comes up tails, and 1 if it comes up heads. And so when x is a binary variable, we often refer to it as either a dummy variable or an indicator variable. So you'll hear either of those terms used. And it turns out that this case is actually quite common. So one case in which you might run a regression and x would be a binary variable would be a clinical trial. So when they're trying to test whether or not a particular medicine or a particular therapy works, then what they do is they get a large group of people and they randomly assign half the people into what we'll call the treated group, where they receive the medicine or the therapy, and then the other half of the people end up in a control group where they either receive nothing or maybe some sort of placebo or something like that, right? And what you want to see is basically whether or not assignment to the treated group has an impact on some sort of clinical outcome relative to assignment in the control group. So you want to see how the average value of y changes as x, which is assignment to the treatment group versus the control group, changes. So in that case, we'd probably code x as a binary variable where x would be equal to 1 if patient I were assigned to the treatment group, and x would be equal to 0 if patient I were assigned to the control group. Alternatively, you might be interested in figuring out, say, what the wage premium is for males or what the sort of wage disadvantage is in the overall data for females. So if you're looking at the relationship between y and between say earnings, which would be the variable y in this case, and gender, which would be x, x would again take on just two values, 1 if say you're female and 0 if individual I were male. So again, x would be a binary variable, and we call either dummy variable or an indicator variable. You could also think about looking at the relationship, say the return to higher education or something, or going to college. So you could look at the relationship between wages, again being y here, and whether or not somebody has a college degree. So in that case, you would code x as being equal to 1 if individual I had a college degree and 0 otherwise. So there are lots of different scenarios in which you might be running a regression where the right-hand side variable in that regression, the x variable, is just a binary variable and only takes on two values. So when it's a binary variable, when it's a dummy variable, it turns out the regression coefficient has a special interpretation. So if we estimate a regression of y on x, if x is binary, then the regression coefficient beta is going to be equal to the difference in means between the two groups. So in this expression here, y bar 1 minus y bar 0, y bar 1 is going to be the mean of yi when xi is equal to 1, and y bar 0 is going to be the mean of yi when xi is equal to 0. So you define two groups based on the value of x, and then within each of those groups, you take the mean of the outcomes. With those two means, you just take the difference in the means, and it turns out that that difference in means is going to be exactly what the regression coefficient gives you if you instead just took all of your data and estimated a regression of y on x. So in the clinical trial example that I mentioned, the difference in mean outcomes, or this expression y bar 1 minus y bar 0, would be the difference in mean outcomes between the treated group and the control group. So what this is saying, so I think intuitively, even if you hadn't taken this class or any econometrics or anything like that, if I told you that you had a clinical trial where a bunch of people had received a treatment and a bunch of people had received a placebo, and I wanted you to estimate the average effect of that treatment on, say, the cholesterol level or something, I think that most of you probably intuitively realize that, okay, if I have data on cholesterol levels, then the way that I would probably want to go about estimating that effect is to figure out what the average cholesterol level was in the control group after the intervention or the clinical trial, figure out what the average level of cholesterol was in the treatment group, and then take the difference between those two averages. So that that procedure of taking the difference in means turns out to be identical to taking all of your data and defining this variable x to be equal to 1 when individuals in the treatment group, 0 when they're in the control group, and then regressing y, which is the cholesterol level in this case, on x. The value of the slope coefficient you get there, beta, is going to be exactly equal to the difference in mean cholesterol levels between the treated group and the control group. In the gender example then, what the regression would be estimating would be the difference in mean outcomes between males and females. So for like the outcome were wages, then you'd be taking like the average male wage and subtracting off the average female wage and figuring out what that difference is. For education, like the outcome were education, then same thing, you take the average education levels for females in your sample, average education levels for males in the sample, and take the difference between those two. And so doing that difference in means is going to give you the exact same answer again as just running a regression of y on x, where x is a variable that is coded as 1 if you're female and 0 if you're male. And in the college example, the regression coefficient is going to give you the difference in mean wages between college graduates and non-college graduates, which incidentally is going up over time. So in these cases, then we refer to the slope coefficient in regression beta as being the difference in means. So it's interesting. They also says September 2001 on it, just before, that was like right when I entered the PhD program. So it's easy enough to just estimate differences in means. You could do it with regression. You could even if you just had like data in Excel or something, you could use the Excel functions to figure out the average wage for females and the average wage for males and take that difference between them. But estimating causal effects is much more different, because whether or not your regression estimate or your difference in means is going to have a causal interpretation is basically going to come down to a question of whether or not this variable x here whether this is correlated with other things that might affect the outcome. And so in like in terms of this equation, basically what's going to matter is whether x is correlated with EI, which are the other things that potentially affect the outcome. And so there's this quote that I got several years ago from the Taiwanese government first etiquette page, which I think demonstrates some of the challenges to trying to conduct causal inference. So the quote says, likewise, it's best not to give a handkerchief as a present. Being something that is used to wipe away tears will actually bring them some kind of bad fortune that is cause for crying. So this kind of demonstrates that the tendency to confuse correlation with causation is one that spans many cultures and eras. I think we can safely assume that gifting a handkerchief is not going to cause serious misfortune. It's true that the use of the handkerchief is in fact correlated with misfortunes, but that's not the same as saying that if I come in and give you a handkerchief, then that's going to cause you to have some sort of misfortune that you otherwise would not have had. Nevertheless, as I said, the handkerchief use can be correlated with unfortunate events. So I agree that it is a superstition, and I'm just saying that the superstition is based on correlations rather than on a well-formed causal model. So I'll give another example shortly. So I think like in that case, it's really easy to say, okay, well, we're interested in looking at causal relationships between variables. Here's a case where we have correlation between two variables. So basically, like one of the variables is handkerchief use and the other variable is misfortune occurring. And there's definitely a correlation, but clearly there isn't a causal relationship running from handkerchief use to misfortune. But in other cases, it can be a little bit trickier to sort of define or conceptualize exactly what it is that we mean when we say one variable has a causal effect on another. So when we say so I want to sort of try to define that a little bit more precisely. So the causal effect of x on y is the change in y that we would expect to observe if we had what we could think of as being an experimental manipulation of the variable x. So the idea here is let's suppose that we increase x by 1 unit without changing anything else that affects y. The resulting change in y that we might see, at least on average, would represent the causal effect of x on y. So sometimes, like maybe in your other econ courses, you might have heard people refer to this type of effect as a ceteris paribus, change in x. So that's Latin for all other things held constant. So the idea is that we're going to change x, but leave everything else that could potentially affect y unchanged. So basically, everything else in this EI term is going to be left unchanged. So in the example that we were using earlier, where x was daily air pollution and y was hospitalizations, the idea is that the causal effect of air pollution on hospitalizations would be the change in hospitalizations that we'd expect to observe if air pollution increases by 1 unit, but nothing else that affects hospitalizations changes. So that's what we mean by a causal effect. Let me just go back one slide here. So something that sort of comes out of this framework is that for some variables, it doesn't really make sense to talk about them having a causal effect on other variables. Okay, so like think back to the 3 examples that I just gave earlier. So one was an example where we're looking at like the relationship between whether or not you get a treatment and your cholesterol level. Another is an example where we're looking at the return to getting a college degree. And then a third was an example where we're looking at, say, the gender wage difference, right? So in the first 2 examples, I think it's pretty easy to think about what the causal effect of the right-hand side variable on the outcome would be, right? So like with the treatment, we would think the idea here is that we're going to give some people the treatment, we're going to give some people like a placebo, and then we're going to see how much their cholesterol levels change when they get the treatment versus when these other people get the placebo, right? So that's pretty straightforward. Likewise with this, with like estimating the return to higher education, you could think about sort of having a case where you had a bunch of people who were like considering going to college, and so for some of them you give them a scholarship and compel them to go, and for others you somehow like prevent them from going to college. And if these 2 groups of people are otherwise comparable, then you could think about basically figuring out what the effect of going to college was on their earnings by collecting a bunch of earnings data for them later on and then computing the difference in means. So in those 2 cases, it's pretty easy to, I think about what the causal effect would be. With the gender example, though, it's not at all clear. And so actually, like in this sort of statistical model that we use and that we teach the graduates, we can't really talk about like the causal effect of gender on wages, right? Because you can't sort of think about a case of like, okay, well, what's going to happen if I change somebody's gender from male to female while holding all other things about them constant, right? So like, I mean, this is the San Francisco Bay Area, so I guess you could think of that in the sense that you could be testing like the effect of some sort of gender reassignment surgery, so basically, sex change. But that's not really what people are sort of interested in when they say like, oh, is there sort of like discrimination against females in the labor market that results in them having lower wages, right? So it's not clear what it would mean to take somebody who's male and then sort of like quote unquote keep everything else about them constant while turning them into a female or something like that. Because you can sort of think back to like, well, what if they had been born female instead of male? Like, what if there had been XX chromosomes instead of XY chromosomes? But even in that case, it's like, well, it's not just the sex chromosome that's changing. Like other things could be changing as well. And then they're developing, their entire sort of like life development course would probably be different because society has sort of different expectations and roles for males and females and so forth. And so there's some question of like, well, how much do you want to sort of quote unquote hold constant about that person versus allow it to change? So it's really not. In some cases, it's not really. It's all sort of like the conceptually talking about the causal effect of some variables doesn't even really make sense within our framework. That being said, in this class, we'll try to concentrate on variables for which it's more straightforward to think about what the causal effect of that variable would be on an outcome. Okay, so let's say that we have a bunch of data on x and y, and we want to estimate the causal effect of x on y. It turns out that in general, a regression of y on x does not estimate that causal effect. So as I said the last lecture, regressions can in fact be used to make what we call descriptive statements. So in our air pollution and hospitalizations example, we could use regression to say, look, when air pollution is high, hospitalizations also tend to be high. That's a perfectly valid and safe statement to make given the scatter plot that I showed you. Of course, that's fake data, but assuming that they were real, it would be totally valid to make that statement. But that doesn't imply that the regression estimates the effect of a ceteris paribus change in x, because it's likely that when air pollution is high, there are other factors that affecting hospitalizations that also tend to be high. So for example, if you just look at the data, it'll become apparent that air pollution, in terms of at least ozone levels, tends to be highest on hot days. And it's also the case that if the temperature gets really high, people can get heat stroke and heat exhaustion and so forth, right? So just saying, well, when I look at the correlation or when I run a regression of hospitalizations on air pollution, I find that hospitalizations tend to increase when air pollution is higher. That doesn't necessarily prove that air pollution has a causal effect, right? Because one explanation is that, okay, air pollution is having a causal effect. The other explanation is that there's this other variable sort of running around behind the scenes, which is temperature. And it turns out that on hot days, air pollution tends to go up, and also people tend to get heat stroke. And so you're seeing this correlation here, but it's not actually because of the air pollution. It's because of this other unobserved variable, which we often refer to as being omitted variables bias. So in that case, the regression coefficient is confounded by other factors that are changing as pollution changes. So to give another example of the difference between ascribing a descriptive relationship to or descriptive interpretation to the regression coefficient versus a causal interpretation, you can think about a case with my cat. So my cat is generally quite well behaved, but she can get agitated and sometimes she'll sort of like bite at you. And if you have like experience with cats, you'll know that generally it's not like, so when dogs are wagging their tail, that usually means that they're like very happy, right? And usually with cats, if they're like twitching their tail really fast, then that means they're like more sort of like in hunting mode and are more likely to bite or scratch you. So if you sort of collected a bunch of data observing my cat, you could have an outcome, yi, being whether or not my cat bites me, and the right-hand side variable in your regression, xi, could be whether or not she's like twitching her tail quickly, right? And so I guarantee if you ran that regression, so you like sat there and collected data over like many hours or days or whatever, got it, and then ran a regression of y and x, you would find that in that regression, beta would have a positive coefficient. So that would imply that on average, if my cat, so let's say x equals 0 means that she's like not moving her tail, and x equals 1 means that she's like twitching her tail. So on average, when she's twitching her tail, you would find that she's more likely to bite me than when she's not twitching her tail. So that would be, so you run that regression, you estimate that relationship, that would actually give you like the conditional expectation of biting, conditional on whether or not she's twitching her tail, and applying a descriptive or even a predictive interpretation to that would be perfectly valid. So then you could say, well, you know what, Professor Anderson, I'm going to say that if she's twitching her tail, then you probably should not like try that or something because she's probably going to bite you. And that would be totally valid. What would not be valid, or where you go wrong, is if you then try to ascribe a causal interpretation to the regression coefficient, right? So the causal interpretation says that, okay, well, I'm going to assume that this coefficient that I estimated as positive beta represents a causal relationship, and so that means that basically if I manipulate x, if I make exogenous changes to x, then y is going to change. So that would be like, you observe her like twitching her tail really fast, and you'd be like, well, you know, I ran this regression, there's a positive coefficient, so I think if you stop her from twitching her tail, then she's not going to bite you. So if you like grab her tail and hold it so she can't twitch anymore, then you know this regression that I ran, which I think represents the causal relationship, implies that it's going to be unlikely that she'll bite you. Common sense would dictate that probably is not going to be true. In fact, not only would she be likely to bite me, but she'd be even more likely than she was before. So that's sort of like a very maybe extreme example, but I think sort of a very representative example of how a regression coefficient could be valid for predictive purposes, but you wouldn't want to ascribe like a causal relationship to it. Okay, so in order to actually ascribe a causal relationship to the, or causal interpretation to the regression coefficient, essentially what you need is that this variable x needs to be as good as randomly assigned. So in social sciences, as in medicine, the gold standard of evidence is in fact what we call the randomized controlled trial. So this is like the clinical trials that I described, where you take a group of people, you essentially flip a coin for each person. If the coin comes up heads, then you assign them to the treatment group, and if the coin comes up tails, you assign them to the control group. So the reason that the randomized control trial, which we call the RCT, the reason that is in fact the gold standard of evidence is that basically it allows you to isolate the effect of x on y without having to worry about whether there are other things that are correlated with x that could be affecting y. So remember, the causal effect of x on y is the change in y that we observe when changing x without changing other factors that affect y. And so in order to estimate this, we need changes in x that are going to be uncorrelated with any other variables that affect y. And the best way to guarantee yourself of that is to randomly assign different levels of x to different people. So like in a lot of our cases, x really only has two levels. Either you're treated, so you have x equals 1, or you're not treated, so you have x equals 0. So the idea here is we're going to randomly choose some people to get treated and other people not to get treated. And because of the random assignment, you know that nothing else can be correlated with x unless x actually has a causal effect on that other thing. So then when we observe changes in x, when we know that x has been randomly assigned, we know that at least on average, other factors that affect y are not changing with x. Because if they were, that would imply that they were correlated with x. And if they were correlated with x, then x was not randomly assigned. So a clinical trial of the drug, I think, is sort of the best example of a randomized controlled trial. As we said before, you know, in that case, you usually code x as being equal to 1 if you're in the treatment group, or if the individual's in the treatment group, and x is going to be equal to 0 if they get assigned to the control group. We know that since x is a dummy, the regression of y and x is going to measure the difference in means between those two groups, the treated and the controls. So if we were studying whether a drug reduces blood pressure, then the regression coefficient would measure the difference in average blood pressure between the treated group and the control group. And again, since x is randomly assigned, we know that on average, all other factors across these two groups must be identical, at least in expectation or on average. Now, that's not the same as saying every person in the control group is exactly like every person in the treatment group, because of course, you know, there's heterogeneity of people, everybody's different. But the idea is that as you get a larger sample, any of the differences will end up averaging out between the two groups, because nothing systematic should be correlated with which group you get assigned to due to the randomization. So that's what we'd like to do in most cases, but unfortunately, in a lot of social science settings, it's infeasible to conduct randomized control trials. So it's changed over the years. I mean, you see more randomized control trials now than you did, I don't know, a few decades ago. And it's particularly true if like you've taken any development economics courses. There's a lot of types of interventions that they'll go and test in developing countries. So not just like clinical things, but things like related to education or something else. They have like these, for example, one of the very large randomized control trial that was run over the past, I guess it was probably like a decade or two ago now, but was this thing called Progresa, which is now called Opportunity Bodies in Mexico, where they essentially have these conditional cash transfer programs. So the idea of the program was like, we're going to give you, so first of all, we're going to give you a cash benefit, so it's like targeted at poor people, and then not only we're going to give you this benefit, but we're going to condition the benefit on whether you meet certain criteria. So like you have to make sure that your kids attend school through grade whatever, right? And so the idea is sort of like there's a carrot and a stick almost. That you want them, first of all, you want them to be less poor, so you're giving them some cash, and you also want them to sort of be investing in human capital for their children, so forth, so you're giving them an incentive to keep the kids in school and so forth. And so in order to evaluate the effects of this program on lots of outcomes, basically they randomly assigned which families would get the conditional cash transfer and which were basically the control group where they basically got nothing. So I think there are sort of more randomized control trials happening in social science settings than there used to be, but you know, in general, they're expensive, and in many cases, they're considered unethical. So if we're thinking in sort of like the environmental context in particular, we wanted to measure the effect of air pollution levels on whether or not hospitalizations increase. We couldn't really think about like randomly assigning daily air pollution levels. The EPA would not allow us to do that. So when we could, right, we could build some giant bonfire outside and